Notice that they're tail to tail. Okay, so that means that you're looking at the angle between them. Okay, they're tail to tail. A scalar projection of vector A onto B is just the length of the shadow that is created by that vector onto B. So how do we find the shadow of A on B? You drop a perpendicular from the end of vector A. And when you drop that perpendicular, it's going to show you that highlighted area right there, what the length of the shadow is. And that's all that a projection is. Okay, what's the difference between a scalar and a vector projection? Well, a scalar projection is going to tell us just magnitude, whereas the vector projection is going to also give us the direction. Okay, and the magnitude will remain the same. Okay, so let's take a look at some different types of projection. So you could have a positive scalar projection, and that's going to happen when the angle between A and B is between 0 and 90, not inclusive, 90 not inclusive, right? And 0 not inclusive. You're going to have a zero projection if the two vectors are perpendicular, right? And I think you guys can see that there's no, the only perpendicular to drop is vector A, right? And so there is no shadow on B. And you're going to have a negative scalar projection when you have an obtuse angle. Okay, so between 90 and 180. Is the projection of A on B equal to the projection of B on A? Well, sometimes yes, but not all the time. So let's take a look. So if I'm projecting A on B in the first case, well, then we see that that magnitude is actually longer than vector B. So let me just show you where I'm looking. Right here. Do you guys see that? That projection is longer than the magnitude of B, vector B. Now, if I want to find the projection of B onto A, well, then I have to drop my perpendicular this way. And you could just redraw this if it's easier for you. That's not a big deal. You could put A now here, and you could have B, which is shorter. We do it this way just so that you can see the exact lengths, right? From B onto A and A onto B. All right, and so what you should notice is that the magnitude is a lot shorter, so the projection is not the same. Okay, when will the projection be the same? Well, it will only be the same if the magnitude of A is equal to the magnitude of B. Okay, are there any questions? So what's a scalar projection? What's a scalar projection? Anyone, shout it out. What is a scalar projection?
It's the shadow.
That's it.
Onto another.
You got it. Shadow of one vector onto another when they are placed tail to tail. Okay? Good. Will there be a shadow if the two vectors are perpendicular?
No.
Good. Excellent. All right. Notice, when calculating projections, a right-angled triangle is always constructed. So trigonometry or SOHCAHTOA and/or the Pythagorean theorem can be used to solve for projections. Again, very easy math. Okay? Okay, so let's talk formula. So what is the scalar projection of A onto B? Well, it's the dot product divided by the magnitude of B. Okay, so A dot B divided by the magnitude of B. So where do you think that comes from? Where do you guys think that comes from? Here, let me now write it in another form. Okay, good, from dot product. So what's another way to write dot product?
Magnitude of A times magnitude of B times cos theta.
Good. We're talking geometry, so he gave me the geometric formula, which is good, rather than the algebraic one. And what do you notice happens here?
Cancels out.
Yeah, good. And so this is the formula. Now I asked, where do you think it comes from? So where do you think this comes from? What do you guys think? So take a look. Where do you think that the scalar projection might come from? Something very simple.
Cosine law?
Not cosine law, but I know what you mean. SOHCAHTOA using cos of theta. Is that what you meant to say? I think so.
Sure.
Yeah, because we know that cos of theta, right, is going to equal the adjacent side, which is the projection, over the hypotenuse. And so if you rearrange that formula, you get the magnitude of A times cos of theta. All right, so, ooh, this looks weird. Hold on one second, what happened here? Okay, so let's fix this. Does yours look like this, guys, when you printed it? I hope not.
No.
Okay, good. Oh, is this gonna delete the whole thing? Let's see, yes it will. Okay, so I want you to ignore, I'm gonna cross it out. And I'll fill in the blanks, okay? So, the vector projection. So now we're talking about the vector projection. So the only difference is now we want to know the direction. And so I don't want to change the magnitude. We know that I can't change the magnitude. The scalar projection is what it is. But I want to now talk about direction. So what I'm going to do is I'm going to multiply by this. What is this? It's the unit vector. So what's happening here now is I'm showing the direction without changing the magnitude, because what's the magnitude of a unit vector? It's just 1. Okay, do you guys see that? So I've got the scalar projection of A on B, which is exactly what we did in the first part. And then I just multiply by the unit vector in the direction of B to get the vector projection. And I'm going to rewrite this. And for those of you that know what the cross product is, this is not the cross product. This is just multiplication. So rearranging this, guys, you get that, right? Magnitude of B times the magnitude of B is the magnitude of B squared. And then there's my vector B. 1 times A dot B is still just A dot B. Are there any questions so far?
Can't you simplify, or is that not a good idea?
This is the formula that we use. What do you want to simplify here? You want to change it to
but-
magnitude of A times magnitude of B cos of theta? You can. Yeah, you can. It's not a big deal. We're going to do it. Yeah. So basically what I'm trying to show here, what you're trying to show here is that it's the exact same formula as above, but just multiplied by the unit vector, which you're right. We simplified this to the magnitude of A cos of theta. So we can do the same thing here. What's going to be left?
Just the magnitude of A cos theta times B over the
What if,
magnitude of B.
yes, excellent. So you're going to be left with 1 magnitude of B because one of them is going to cancel. You're going to have magnitude of A times cos of theta in the numerator times your vector B. Okay, good. So this is a scalar, correct? This is just a number, no vectors in here. When we do the dot product, we know the result is always a scalar. Good. Okay, so in 3D space, just to see it a little bit more clearly, here I've got vector A and I've got vector B, and the projection is that highlighted area. And what you notice that it's by dropping a perpendicular there. Okay, good. Any questions? Okay, so let's do the first example. For vectors A, 2, -1, -5, and B, 6, -2, 1, calculate the following scalar projections. So we're just going to use the formula. Now, in this case, am I going to use the geometric formula or am I going to use the regular formula? What do you think? We have 2 formulas there. We saw magnitude of A cos of theta, and then we saw A dot B divided by the magnitude of B. What do you think I'm going to use in this case? I have components, so I'm going to use this one. So I need to find the magnitude. How do I use the dot product? What's A dot B? What do I do?
Times the components and add them.
Yes, exactly. Multiply your first component, both of them together, add it to the product of the second components, add it to the product of the third components. Beautiful. And I'll just write that here. Divided by my magnitude of B. Okay, who wants to do that for me? So go ahead and multiply and add. So what am I going to be left with? 12 plus 2 minus 5. And for magnitude, what do I do?
Square each component and add them.
Excellent. Sum of the squares. Sorry, guys, just give me 1 second. Yes, question? In 10 minutes, okay? And actually 12 minutes. In 12 minutes, you're going to go. Corey's going to help you, okay? So 12 plus 2 minus 5 gives me 9 over 41. And sometimes you might leave it as exact, and sometimes you might give it as a decimal. It all depends on what I ask for in the question, okay? And it's a scalar. What else did I want to say? And you're never rationalizing. You can leave it like that. Okay, so now let's do B on A. So now we just do it the other way. And is this necessarily going to be the same? No. It will only be the same if the two vectors have the same magnitude. Okay, so A dot B, B dot A. Is there going to be a difference there? Does it matter if I do A dot B or no? Good. What law do we call that? What do we say? Dot product is, who remembers what that law is called?
Commutative.
Yeah, good. Commutative. Very good. Okay, commutative. So now, the only thing that changes is now I'm dividing by the magnitude of vector A. And so the magnitude of vector A is going to be 4 plus 1 plus 25. So what do you guys think? Are the magnitude of A and B the same?
No.
No, they're not. Very good. Any questions? Okay, again, scalar projection, we end up with just a number. Find the vector projection now of OA, 2, -1, on OB, 4, 2. What do I do? I want the vector projection now. So what do I do?
Use the formula.
Yeah, you're going to use the formula. And essentially what you should realize is you're doing the exact same thing that we just did. The only difference is you're going to be multiplying by a unit vector. Okay, and it's going to be the unit vector OB because that's the direction that we want. Good. So using the formula. So in this case, would I use the geometric formula or would I use the algebraic formula? What do you guys think? Well, I'm given components. So if you're given components, you're going to use the dot product. You're not going to use cos of theta.
Miss Jocelyn's here.
Oh, nice. Thank you. Okay, let me finish this and then I'll I'll update my attendance, okay? Okay, so doing dot product. So I'm not going to write my components in. I'm just going to do it. It's 2D space, nice and easy. Who can tell me what I get here? Doing my dot product, what do I do? Oh,
8
guys.
minus 2.
Yes, good. And then divided by? Give me 1 second, guys. I'll be right back, okay? Give me 1 second. Yeah. Guys, is it almost time for you to go on? You're watching the time? Okay. Oh, boy. Sorry, guys, someone was at my door. Okay, so magnitude of OB, vector OB. So what do? Well, we take 4 squared and add it to 2 squared, right? And so here I'm going to have, oops, what am I missing?
Squared.
Yeah.
And the OB on the right.
Yeah. Squared. And then I'm multiplying. Okay. And now I'm multiplying by OB, vector OB. All right, and so I have 6 over 20. It's the square root of 20 squared, right? So it's just 20. And so here I have 3 over 10. I'm going to reduce it. Which will give me 6 over 5, 3 over 5. So what do we call this form? What is this form called?
Component form.
Good. So here's component form. What other form can I show it in?
Standard basis form.
Excellent. Cool. Any questions? Good. Okay, so now we're going to talk about the direction angles and direction cosines. So suppose we project the position vector OP on each of the axes in R3. So let's take a look at our diagram here. So here's OP. It's my light blue, bluey green, aqua, whatever you want to call it, resultant. That's the vector there. And basically, we want to find out the angle that it makes with all 3 of the axes. So with the x-axis, with the y-axis, and with the z-axis. And so you have very simple formulas that you're going to use to find that. So the direction angles are the angles between the vectors P, A, B, C, and the axes, as I just said. When you're talking about the x-axis, that angle is called alpha. We don't use theta, we use alpha. When we're talking about the angle between that position vector and the y-axis, we use the Greek letter beta as our angle, and we use gamma. And gamma is like this, like that. I don't know why it's going crooked on me. Okay, are there any questions so far? And I want you to notice, guys, as always, we're always dealing with angles between 0 and 180, okay? All right, so here's the picture of all the angles, alpha, beta, gamma. And here are your formulas. So if you're looking for the cos of alpha, so that means with the x-axis, well, then you're going to take the component, your first component, your A component of your position vector, and you're going to divide it by the magnitude of that vector. If you are looking for the angle with the y-axis, then you're going to take your second component and divide it by the magnitude. If you're looking for the angle of gamma, right? So with the z-axis, then you're going to take the C component and you're going to divide it by the magnitude of the vector. Okay? And then to solve for those angles, you know, you take the inverse of cos. Okay? So this is x-axis. Notice you're using that first coordinate, your x-coordinate. This is y-axis. This is x-axis. Okay? And notice here we're using the z-coordinate. Here we're using the y-coordinate. And the first one you're using the x-coordinate. Okay, so example 3. For vector OP, 2, 4, -1, find the angle it makes with the positive y-axis. So I want to know the y-axis, and so that means I'm looking for beta, and so I'm going to use the middle formula. And it's as simple as that. So which component do I use? 2, 4, or -1?
4.
Yeah, I thought I heard 4. Very good. And then over the magnitude of your vector. It's as simple as that, guys. Very, very simple math. Okay. And now we want to know angle beta, so we take the inverse of cos. And what do we get here, guys? Can somebody calculate it for me to 1 decimal place, please? Okay. start getting me on because the teacher already.
29.2.
Perfect, Nicholas. Thank you very much. Okay, recap. So in this lesson, we learned what a scalar projection is. We talked about what the difference is between a positive and a negative scalar projection, and we learned that when two vectors are perpendicular, there is no scalar projection. Here's the formula for your scalar projection. And we learned that for the vector projection, it's the exact same formula, but you're multiplying by the unit vector of that second vector, the one that you're projecting onto. You need the direction of that one, right? Because that's going to give us the direction of the shadow. Okay. We learned that the direction cosines means that we're finding the angles between a position vector OP and each of the three axes, and these are the formulas. When you're looking for the angle alpha, we use the first component over the magnitude of OP. When you're looking for beta, we use the second component, your y component. And here we use our z component. Okay? And
Miss, I have a question.
Yeah.
For the example you gave us, you said to find the angle between the positive y-axis and the position vector.
Yes.
So if you ask for the angle between the negative y-axis and the position vector, is it just 180 minus the angle that we find?
Yes. So hold on one second. Let me go back. Okay, so here, so if I wanted between the negative, I'm going to try to draw this. It would be that way. And so, yes, it would be 180 minus, as you can clearly see that by opposite vectors that these are equal, correct? That's our opposite vectors, opposite angles. Do you see that?
Okay, thank you.
Cool. Hold on a second. This is not correct. There you go. Opposite angles. Cool. Okay. And this is your homework for this section, guys. Page 398, numbers 1 to 6, 7AC, 8 to 13, and 15. No errors that we know of in this section. Of course, if you find any that you think maybe, let me know. And that's it. So we're going to do 7.6. I think we're going to take a little break. Let's take a 15-minute break maybe, or a 10-minute break. I don't know. What do you guys prefer? Let's say 10-minute break. Let's take a 10-minute break. So we'll be back at 1:10. Okay, so 1:10, guys, meet me back here. Go get a drink of water, go to the bathroom, just stretch your